Okay, I'm going to start. Our goal today is to derive the cable equation and then solve the cable equation for voltage as a function of space and time so that we can use it to understand how neurons signal within their dendrites. So we're going to go to work on the cable equation now. So this is where we left off Wednesday. We were going to approximate a dendrite as a single long cable. We're taking that cable and we're breaking it into very small chunks of cable, each delta x long. Delta x is going to be small. We went through how each one of these little cable elements has an electrical circuit representation. So this element here is represented electrically as an axial resistance. And this element here corresponds to transmembrane resistance and transmembrane capacitance. So current can flow along the core of the cable, or it can leak out through the surface membrane of the cable. And the values of these resistors and that capacitance we worked out Wednesday. We derived the formulas for those capacitor and resistor values. So now we're going to derive the partial differential equation in terms of V of x and t, voltage as a function of space and time. So looking at this circuit, if we're sitting at this node V sub I, the potential at that node is equal to the potential at this node, V of I minus 1, minus the voltage drop induced as current flows along the core of the cable through the axial resistance. And so that voltage drop is this term here. So V sub I, that voltage, equals this voltage minus this voltage drop, and that voltage drop is determined by the axial current at that location and the resistor and the value of that resistor. It's just Ohm's law, okay? So that's the voltage drop. So let's delta VI be V of I minus V of I minus 1. It's that voltage differential. It's just equal to this. So now if we divide both sides by delta x and let delta x get very small, what we obtain is that the partial derivative of v, and note here that v has as arguments space and time. X indexes space, t is indexing time. I'm not writing all of that down, but v has arguments x and t. So the partial derivative of v with respect to x is just equal to this term here. And so multiplying through by this inverse, we get an expression for axial current. This current is proportional to the voltage gradient at that location. It makes intuitive sense. This is just Ohm's law. Current equals voltage times conductance. And so this is the voltage term, this is the conductance term. So the axial current satisfies this relationship. So we're going to hold this relationship in mind, and we're going to come back and use it later as we work towards formulating the cable equation. All right, so we're going to now work out another relationship that with that equation 1 will give us the cable equation, and we're going to get this relationship by applying Kirchhoff's current law at this same node. So Kirchhoff's current law says the current flowing into a node must be balanced by the current flowing out of that node, and there are two ways for that current to flow out of this node. So if the current's entering here, it can either flow in this direction, so that's the term I sub I plus 1, that's this current here, minus the current that flows through the capacitive and the resistive transmembrane elements. So an entering current must be balanced by the current, the sum of the currents leaving the node. You can't have charge accumulation at a node. That violates conservation of charge. That's Kirchhoff's current law. Okay, so if we do that, if we compute the change in current, the delta I, to be the current leaving this node minus the current entering that node, well, that change in current, there's only one way for there to be a difference between this current value and this current value, and that is current is leaking out through the membrane. So this current differential must equal the current that is flowing through the resistive element, that's this term here, plus the current that's flowing through the capacitive element. And the current through a capacitor is the capacitor value, which is this term here, times dV dt, the time rate of change of voltage across the elements of the capacitor. So if voltage isn't changing, there's no current through the capacitor, there's only current through the capacitor when voltage is changing. So this relationship must be true, and that follows from Ohm's law. Okay, so now we've got two relationships. The first equation we worked out this new equation, so I'm just representing that new equation here. It was equation number 2. So this equation gives us an expression in a derivative of current and voltages on this side. We don't want there to be two variables in here. We don't want current and voltage. We want an equation in voltage alone. We want the left-hand side to have voltage terms, the right-hand side to have voltage terms. If we get things in that form, then maybe we can write a partial differential equation for voltage, because that's the only variable it will have in the equation. So we go back to that first relationship we derived for the axial current, right? So if we take the partial derivative of that with respect to x, we get this, right? And so let's plug this into here. Then on the left-hand side, we'll only have terms in voltage, and on the right-hand side, we'll have terms in voltage. That's what we want. It's just that the left-hand side is the second spatial derivative of voltage. The right-hand side involves voltage and its first derivative with respect to time. But if we make this substitution, then on the left-hand side, we'll have the second spatial derivative of voltage when we plug this in here, and we go through all the algebra. We find that the second spatial derivative of voltage must equal this term. So there's equality here. And so we have this relationship. If we multiply both sides by the inverse of this term, we've got this coefficient multiplying that second derivative must equal voltage plus this constant of proportionality times dV dt. That's the cable equation. It's just in a different form than I showed you originally. It's not dimensionless. X has dimension of space, typically measured in centimeter, because our specific membrane parameters, remember, are in units of ohms per centimeter or microfarads per centimeter. Distance is measured in centimeters. So and there's there's a time term involved here. There's a derivative of voltage with respect to time. So things aren't yet dimensionless, and to make this equation dimensionless, we're going to consider what this term corresponds to and what this term corresponds to, and that will lead to some intuitively reasonable quantities to use to turn time into a dimensionless variable and space into a dimensionless variable. So let's now so here's the cable equation again, all right? And we're going to do the following thought experiment. Imagine taking a long cable and somehow imposing uniform voltage everywhere along that cable. We can space clamp that cable. At every position X, voltage is the same. Now Hodgkin and Huxley figured out how to do this with the squid giant axon. They took this enormous axon from this beast and ran a wire through it, and were able to inject charge everywhere along that large axon to lock membrane potential in space to be the same everywhere. Now, suppose you do that, and it's called a space clamp, and then at time zero you release the space clamp. You let whatever will happen to voltage happen. You're not locking it to be the same everywhere in space anymore. Tell me how, somebody tell me how voltage will decay in time. How do you think it will decay in time? Yeah. It'll decay exponentially. Why? Give me an intuitive, kind of an intuitive explanation of that. Where does charge go? Is there any axial flow of charge if you do that? There isn't, that's right. Because potential is uniform everywhere. So initially there's no movement, no axial flow of current, no axial movement of charge. The only place for charge to go is out through the membrane, to leak out through the membrane capacitance and the membrane resistance. And it will do so at the same rate everywhere along the cable if the properties of the cable are all uniform, which we're assuming they are. So you have leakage of charge out through the membrane, and whatever happens to potential, it will happen uniformly along the cable. And you're right, it so happens that the way in which that potential drops is at an exponential rate. And you can prove that, and you prove it by assuming we initially space clamp the cable at some uniform voltage. So the gradient of voltage is 0. So the cable equation turns into this equation. 0 equals the voltage term plus a constant of proportionality times the first time derivative of voltage. This is a first order differential equation, right? With an initial condition V0, whatever the space clamp is. You know the solution of that equation. It's an exponential, right? And so this is the way voltage will decay everywhere along the cable. And the key idea here is that the time constant of that decay is the product of the specific membrane resistance times the specific membrane capacitance. It's known as the membrane time constant. Yes?
So intuitively, the reason it decays exponentially is because of the capacitor, right?
It's because the only path for charge to be removed from this cable is through a parallel RC circuit. And that RC circuit has a time constant of R times C. Yeah. So then this time constant, this is the rate at which voltage decays. That rate, that time at which potential decays by 2/3 of its initial value, that's the time constant. That becomes a natural parameter with which to normalize time. So if we now define time as a dimensionless variable, capital T, and let capital T be equal to little t, actual time and whatever its units are, seconds, and divided by the product of Rm and Cm, this thing we call the time constant, then time is measured in units of time constants, and it has 0 dimension. Capital T, when capital T is 1, that's a time corresponding to the time constant. And when it's 2, that's 2 time constants. So T now, capital T, is now a dimensionless time variable, has no units, because we're dividing little t, real time, by this membrane time constant. Okay, so we've decided upon an approach to making time dimensionless. Now we've got to think about how do we make space dimensionless. If space has units of centimeters, we're measuring things in units of centimeters, we want to get rid of that. So we want to define a capital L, our space variable, which is equal to little l, the actual location in space along a cable, divided by something. And that something has to have units of space, units of centimeters. Okay, so where does that come from? All right, so imagine taking an infinitely long cable, this membrane cable, the very same one we're considering here, and injecting current at a point and applying that current and waiting until voltage achieves its steady state value everywhere along the cable. So now imagine looking at the spatial profile by which voltage decays away from the site of current injection. So we're waiting a long time, we're injecting this constant current, things settle down, there's some spatial profile. What is it going to be? Again, it's that spatial pattern of voltage is going to decay at an exponential rate in space along the cable, right? And so it's going to have its largest value, the voltage value will be largest where the current is injected, and as we move away from that injection site, the profile of decay is that of an exponential. And we can prove that. This proves that. So if we are thinking about steady state responses, by definition steady state means dV dt is changing. I'm sorry, dV dt is not changing. It's zero. Everywhere along the cable it's zero, so this term goes away and we're left with this second order differential equation which has this solution. Remind yourselves of that, prove that to yourselves by substituting this solution into this equation. So there's a term lambda here. Lambda is known as the space constant. It's the value, it's the position, it's how far away we are from the site of current injection where voltage has decayed by roughly 2/3, right? That's the space constant. And the space constant is given by this term here. So if you go through this derivation, you'll see that the space constant is equal to the specific membrane resistance divided by the specific axial resistance defined on Wednesday. Little r is the radius of the cable here in centimeters. And so this value, this number, the space constant, it's got a value and it's in units of centimeters. It's got some value. And so if we now normalize distance by this number, distance is now a dimensionless variable and it's measured in units of this space constant. So when capital L, our dimensionless variable representing our new distance, has value 1, that means we are one space constant away from another location. So when it has value 2, we're 2 space constants away. So using these normalization factors, if we now define capital L equals little l real distance divided by the space constant, capital T equals little t, the real time, divided by the membrane time constant, like shown here, and we plug it into that cable equation that I showed you earlier, the parameters go away, and we're left with a partial differential equation in just voltage as a function of space and time, but now the space and time variables are what you see here. They're dimensionless. So that's the cable equation. It's one of the most heavily studied partial differential equations in existence, and it's got a really simple form. All right? Now, to figure out profiles of voltage in space and time in this ultra simple model of a dendrite, just a cable, we've got to solve this equation. So Will Rall went to work and figured out all of the different ways in which we could solve this equation that are useful, that give us useful, meaningful results. So that's what we're going to turn to now. So, rather than thinking now about a cable of infinite extent, we're going to define this cable as having uniform properties everywhere, but now it has a fixed length. And in our dimensionless length parameter, capital L, we're just going to say it has some length, capital L, right? Now, if we were to inject current into one end of this cable, we will observe in the steady state some voltage that I'm calling V0. So voltage times input conductance equals the current flowing into the cable from Ohm's law, right? And so what we need to do to compute the voltage in response to this current is we need to know the input conductance of this cable looking into this end, right? What is the resistance, or the conductance, I should say, to current flow looking into this end of the cable? If we know that and we're pumping in a current of this value from Ohm's law, we can calculate the voltage at that end of the cable. That's pretty trivial. It's pretty basic, right? And so what Will-Rall proved is that armed with this information, armed with knowledge of this initial voltage, we can get voltage everywhere along the cable. And he put things into a form that's simple to work with. And it turns out that there is an important parameter that is a property of this cable that is needed to solve these equations in order to get this voltage profile. And that parameter is this thing called G out. This unreadable script here is out. The output conductance sitting at that end of the cable. Imagine you're looking out that end of the cable and asking the question, how is the cable terminated, right? So in Wednesday I mentioned this term, the sealed end boundary condition. If the cable is terminated by a sealed end, the output conductance is 0. There's no movement of charge out of that end of the cable. That's a very commonly made assumption in neural modeling because, as I said, dendrites tend to taper with increasing distance from the soma. So this surface area is very small and there may be no channels or a channel within that tiny patch of membrane, and therefore the output conductance is 0. Nothing leaks out the end of the cable. Or maybe that isn't true. For the cable theory, it doesn't matter what the output conductance is. You just got to know it. It establishes a boundary condition. So if you got to know that output conductance. So it's a parameter, but it's commonly assumed to be 0. All right. We're going to work through the way in which Will-Rall addressed this problem, and we're only going to be thinking in steady state responses, not in time domain responses, not about time domain responses. Because while the cable equation can be solved in the time domain, you give me any current profile, any temporal pattern of current, even give me a model of synaptic input to a cable, the cable equation can be solved analytically, pencil and paper, in the time domain. There is a form of that solution. It involves an infinite series, but that solution can be written down. It's just much more complex than steady state solutions. So we're letting time become large, and rather than thinking about v of x and t, we're going to think about v of x, and that just means things are in the steady state. Potentials aren't changing anywhere along the cable anymore. So the general form of the cable equation under that assumption of steady state conditions is this. And these constants C1 and C2 will be determined by boundary conditions on the cable. But Will-Rall kind of knew where he wanted to take this, and he wanted to write these equations in a particular form. And so he used the following construct, that regardless of what C1 and C2 are, you can always pick an A and a B such that your choice of A and B gives you C1 here, and your choice of A and B here gives you C2. So you can just rewrite things in that way. And so now if we multiply this out, and notice that e to the negative capital L is the electrotronic length of the cable. It's just a number, right? So e to the negative L is just some number, just some scaling factor here, and that's what you can always find A's and B's such that this equals C1 and this equals C2. But you need to know the electrotronic length of the cable to do it, so that's a given in these cable problems. And so multiplying this expression out to collect terms multiplied by A and terms multiplied by B, this is what you get when you do that. And he recognized that, oh, this is the definition of the hyperbolic cosine function, and this is the definition of the hyperbolic sine function. So our solution for voltage anywhere along the cable in the steady state has this general form. L is the electrotronic length of the cable. I guess I haven't defined that term. I just used it without defining it, right? I said electrotronic length. So the physical length of the cable divided by the space constant is the electrotronic length of the cable. And that's what we're calling capital L here, right? All right, so that's a given. If I'm going to give you a homework problem in cable theory, I might give you the specific membrane parameters and properties of a cable and its physical length. And to work with these formulas, you'll have to figure out the space constant and divide and express anything having to do with space, like the physical length of the cable, in units of the space constant. So that's this thing, capital L. It's the length of the cable in units of space constants. So we don't yet know what A and B are, but we know that voltage in the steady state anywhere along the cable satisfies this. All right. So we're gonna try and figure out what those parameters A and B really represent, and how do we get them. And so here's the general solution for V. Now I've pulled a fast one on you here. I've jumped out of dimensionless world. I'm back into real space parameters. So little l divided by lambda, that's the capital L in the previous formula, right? And little x divided by lambda, that's capital X. I'm back to working in the real physical space dimension here for a moment. So that's V of x. We're going to take the partial derivative of V of x with respect to x. So that's what it is. And we have already developed an expression for the axial current at any point along the cable and the relationship that it must have to the partial derivative of V of x, right? So we've got this term on the left-hand side. So I know that at location 0, right, dv of x evaluated at location 0 is just I of 0 divided by this thing, right? So I can plug that in for dv of x and get a current on the left-hand side and the rest of this expression on the right-hand side, right? So continuing, if this is the form of the solution for any point x, then at x equals 0, the solution is this thing A times the hyperbolic cosine of L over lambda, x is 0, plus B times the hyperbolic sine of L over lambda, x is 0. So we've got an I of 0 and a V of 0. We've got a relationship on the current going into the left-hand side of this cable at location 0, and we've got a relationship on the voltage at that same location. Why do we care about this? Because we can use Ohm's law now to figure out the input conductance of the cable at location x equals 0. It's current divided by the voltage at that location. Ohm's law tells us that. And so if we divide this stuff by this stuff, this is what we get, right? The input conductance of the cable at location 0 is all this stuff. And if we massage it and divide by the right terms here, we can rewrite this in this form. And look what we've got. The input conductance is a function, hyperbolic tangent function, of the length of the cable. There are a bunch of parameters out here. They're given. In any cable problem I ask you to solve, I have to give you these. You can't solve it. And the ratio B over A appears in this expression. It's determining the input conductance of the cable. So we're getting somewhere. Whatever these A's and B's were, their ratio determines the input conductance of this cable. Okay, so let's keep working on it. Okay, suppose this is a semi-infinite cable. We let the distance, the length of the cable go to infinity. It's infinitely long. Well, if we do that, this term goes to 1. The hyperbolic tangent of infinity is 1. And we're left with 1 plus b over a divided by 1 plus b over a. Hey, that's 1. So we're just left with this stuff, and we know the input conductance of this infinite version of the cable is equal to this term here. All right? So we're going to give this input conductance a special name. If I give you a cable with certain properties and certain electrotonic length, we're going to call this G infinity. The input conductance of an infinitely extended version of that cable is this thing, G infinity. And it equals these terms here. So I'm telling you this. It's not a digression. We're going to need to use G infinity. You're going to need to understand where this term G infinity comes from. Okay. Alrighty, so let's now work at the other end of the cable. Let's go to location x equals little l. It's the right-hand end of the cable. So at little l, right? At x equals little l, v of little l, x equals little l, these arguments are 0, right? So that means that the current at that end of the cable, it satisfies this equation here, is proportional to this unknown coefficient a times the hyperbolic sine of 0, which is 0, so this term goes away, plus b times the hyperbolic cosine of 0, which is 1. And so the current at that right end of the cable, flowing out of that right end of the cable, is equal to this. All right? Now let's go and work on the voltage at that right end of the cable. That voltage is equal to this, and since this is 0 and this is 1, the voltage at that end of the cable is just A. So now I know that if I look at the voltage flowing out of the cable at location L and divide it by the voltage at that location, by definition from Ohm's law, that's what we're going to call the output conductance at the right end of that cable. And so we get it by dividing this by this. And that is this quantity here. Right? So we've now got two parameters that I've explained to you. and we've got this ratio B over A. We can solve for B over A, and it's the ratio of these two parameters that I've just gone through. By definition, this is the output conductance looking out the right end of the cable. We're calling that G out. If we divide that by the input conductance of a semi-infinite version of this cable, a thing we're calling G infinity, that's what the ratio B over A is. We don't need to solve for B over A. We just did it. We know we know its definition. So what does this mean? It means that we can go back to this equation, and we know the input conductance of this finite length cable. We can just go in and replace B over A with this, and this is what we get. So the input conductance of a finite length cable is determined by three parameters. Its electrotonic length, the output conductance, and the input conductance of a semi-infinite version of that cable. We know how to calculate this from the intrinsic cable properties. Here it is. G out is usually a given in any cable problem, and usually it's set to 0. And so we have a relationship for the input conductance of a finite length cable. Yes?
So is this a cable that extends to infinity on the left edge and then cuts off at x equals L on the right edge?
This input conductance is that of a cable that begins at capital X, our normalized distance measure, of 0, and ends at capital L, whatever that value happens to be. Maybe capital L is 1 space constant or 2 space constants. It's just a finite length cable. So this is an expression for the input conductance of that finite length cable. And the expression comes in terms of the length of the cable normalized by the space constant, that's the capital L, and these two other membrane parameters. The G infinity term is the input conductance of a semi-infinite version of this very same cable. So rather than ending at L, imagine it extending out to be infinitely long. G infinity is the input conductance of that infinite version of the cable.
Is that a parameter that we're given or something that we're solving?
Well, you can solve. You'll always be given the parameters here that you need to compute G infinity, right? We showed here that G infinity satisfies this relationship where R is the cable radius, R sub I is the the specific axial resistance of the cable, and lambda is the space constant, and there's another formula for lambda. So and that formula for lambda only depends on specific axial resistance and specific membrane resistance. So everything here can be calculated, and if I did a cable problem, I'd have to give you all of these parameters that are needed to calculate it. So once you have it, you can compute the input conductance of a finite length cable. So armed with that, we can go back to the cable equation now, our steady state solution, and we can express the voltage at any location along that cable, measured in the units of space constants, and we can divide that by the voltage at location 0. So we're injecting some current into location 0 into the cable. It produces that voltage. That ratio satisfies this relationship here. So why do we care about this? If we're injecting current into the left side of any finite length cable at location x equals 0, we can compute V0 if we know the value of the current that's being injected and the input conductance of that cable. That's why I've talked about the input conductance of a finite length cable, because we need it to understand how that cable responds in terms of voltage at the site where current is injected. Okay, are you with me on this? Got to tell me if you're not, because all is going to be lost as we move along, right? So if there's something you're not getting here, tell me. So the reason we derived the input conductance of a finite length cable at location x equals 0 is we need it to compute V of 0 in response to an injected current. And what this relationship says is if you know that voltage at location 0, then all you need to do is multiply it by this stuff to get voltage anywhere else along the cable. So that's what Will Rall did. He derived this result, and he showed how this relationship holds. Now, you're probably thinking, who cares, right? Am I really going to be studying neurons by thinking about injecting current into one end of just a simple cable and trying to figure out and computing what voltage decay is like along the cable? Well, this is why it's important. Imagine you're injecting current not in the middle of this dendrite, not at the end of a dendrite, but somewhere within the dendritic tree. So this current is like a synaptic input on a dendrite. It lands somewhere in the dendritic tree. And your job is to compute how does that current influence potential everywhere within the dendrite of this neuron. You want to get V of x everywhere. How do you do it using the principles that we've derived? Well, it's simple. You do this. Imagine you're sitting here where the site of current injection is. That current comes into the cable, some of it flows in this direction, some of it flows in that direction, right? So electrically that's equivalent to this structure. We've got two cables in parallel. One has this length, L1, right here. The other has this length, L minus L1, right here. We're injecting current here. That current is dividing. Some of it will flow into this structure. Some of it will flow into this structure. So how do we get voltage everywhere along this cable, which is like computing voltage everywhere along this branch of the big cable? And how do we get voltage everywhere along here? It's simple now. We know from the formulas that we've gone through what the input conductance is looking into this finite length cable. It's the formula that we just derived. We know the input conductance looking into this finite length cable. They're in parallel. So the net input conductance seen at this node is the sum of those two conductances. And so now we have the total input conductance of this cable at this location. It's the sum of this one plus that one, right? So if we're injecting a current here, Ohm's law now gives us the voltage here. We've got our V0. And now the formula that I just showed you, V of x over V0, we can now grab that formula and compute voltage everywhere along these two cables, which is equivalent to the way in which voltage decays away from the synaptic input in this direction or this direction. So this is why I call it the geometry of cable problems. It's a clever thing that Will Rall did. He took a really simple model. It seems like many of these relationships that we're deriving are arcane and perhaps not of great value. But when you start to think about how they can be applied to solve some really significant problems. Here we now can, in pencil and paper, solve for voltage everywhere in a simple model of a dendrite, I grant you that, in response to a simple model of a synaptic input. It's just injected current. So we get an idea of how a synaptic input here will influence things in space in this dendritic tree. Here's something even more useful. Here's a branched dendrite model. So it consists of a bifurcating cable. So here the primary dendrite gives rise to two daughter branches. They branch again, they branch again. So there's 1, 2, 3 orders of branching here. Suppose we were to inject current at this node out here, at the very end of this dendrite. So that current injection represents, in some sense, a synaptic input to this neuron. Suppose we want to know the potential that current input, that synaptic input, will generate at the soma. It might be large. If it's large, it could cause this neuron to fire action potentials. If it's small, it might not do anything. The remarkable thing that Will Rawls' work allows us to do is to solve what might seem like it is a complex problem with pencil and paper. This has a closed form analytic solution. You can do this. And the strategy is simple. Well, kind of simple, conceptually simple. It might involve quite a few calculations, but to obtain voltage everywhere along this dendritic branch, what do we need to know? We need to know the intrinsic membrane properties of the cable forming that branch, and we need to know the output conductance when we're sitting here at the end of this dendritic cable looking into the rest of this structure. We need to know that input conductance. If we have that, we can figure out voltage everywhere along this cable in response to that input. So the question is, how do we get that output conductance? Well, it can be done. And the way you do it is you march out to the tips of these dendrites and you ask yourself, what's the output conductance looking into these two cable structures here? You can calculate that using the formulas that we've derived. It's the input conductance of this cable plus the input conductance of that cable. You got it now. Then you march over here and you say, what's the input conductance of this cable when it's terminated with these two structures? Well, this input conductance plus this input conductance is what we've called the terminating output conductance on this cable, right? So now you know how to get the conductance looking into this branch when it's terminated by these branches. So you just do this. You just sweep through the dendritic tree and you compute the output conductance looking into each of the nodes involved until you march all the way back here. And you finally get the output conductance looking out of this dendritic branch. It's the input conductance of this entire dendritic tree plus the input conductance of this one cable. But the thing is, you can calculate that. And you get it by going out to the dendritic periphery and just doing iteratively the thing that I just said. You iteratively compute input conductances at each dendritic branch point. And you'll finally march your way all the way back here, and you'll have everything you know to compute voltage along this cable. So now you've got a voltage here, and you have to be told something about the terminating output conductance on this branch, or you're stuck, right? So let's say that output conductance is 0. Well, okay, now you've got voltage everywhere along that branch, right? And now what matters is the input conductance of this structure sitting here. You've already calculated it. You had to calculate it to get that value here, right? So write it down, remember it, and use it to calculate voltage everywhere along this branch. And you can go through the entire dendritic tree and pencil and paper. You can figure out how a synaptic input anywhere in a dendrite influences anywhere else in the dendrite. I think that's remarkable. This is what Will Rawls did. Pencil and paper, no computing. Now we'd be done with computing, obviously, but he got there by making the problem as simple as it could be and getting at the essence of it. And so, okay, hey, I didn't start my timer again, but it's 2:17. That is the essence of, that's the core of cable theory and why it's important. It enables you to do these remarkable calculations about how synaptic inputs influence other dendritic sites. Now, it's still used today, even though this is a theory developed years ago. Here's a recent study of pyramidal cells, and here are some images of these pyramidal cells, and you see there's an upper part, so these pyramidal cells extend through different layers of cortex, okay? So as we're moving deeper into cortex, that's this distance here. So this is deeper in cortex, this is superficial in cortex. Each pyramidal cell has an apical part, the part closest to the outer surface of the brain, and a basal part. And that's the cell body where there's a dendrite that comes off that starts the apical branches, and there's another dendrite that comes off that starts the basal branches. So they're colored blue and red. And obviously, if you look at these dendrites, the dimensions of the pyramidal cells are changing, right? These basal dendrites don't look so different as a function of depth, but the apical dendrites are getting longer. And so this investigator asked the question, well, they look like they're longer, but are they electrically longer? So how do you answer that question? You need to compute the electrotonic length of that dendrite. You need to understand how physical length relates to the inherent space constant of that dendrite. This is a concept from Will Rall. So they did this, they calculated it. They had to make assumptions about what specific membrane resistance and axial resistance were to get space constants. So they did that. And yeah, it's an assumption. But they showed that electrically, in terms of electrical length, these apical dendrites were longer the further down you go in cortex than the further up you are in cortex. So even though this theory came out 1960-ish, 50 years later, you still see how these notions are important in computational neuroscience and still being used. This is a 2017 paper. It's a relatively recent paper about dendritic structure and organization. So this is the legacy of Will Rall. It is said that Will Rall established the modern concept of the neuron, and that modern concept is in opposition to what Sir John Eccles said. It is that when you actually do things mathematically and understand the question mathematically and use these principles, the electrotonic distance, the electrical length of dendrites is shorter than people thought. And even distant inputs on a dendrite can have important effects on the soma and action potential generation. Sorry, Sir John Eccles, you lose in that regard, but he won in other regards. He's got the chemical theory of synaptic transmission and a Nobel Prize, and Will Rall didn't get a Nobel Prize, but we remember his work for sure. So we'll look at even more significant applications of his work in the next lectures. See ya.